So today we are very happy to have our own Oleg. In the meeting, he will be talking about geometry and algebra of deflections.
Thank you very much. Let us speak here. I promised that the talk will be elementary. Most of the material on that hand is absolutely new for me. I mean that probably a few first slides I used in geometry course here. But and all these things appear because I reflections today will be mainly reflections in 2 and 3 dimensional space. Usually 3 dimensional. Certainly, this can be generalized to like a boric situation, to project it into some others, and I hope that it can be generalized much more. But it is still a work in progress. But I want to start with absolutely standard material, because there was a long period of time in the United States when the subject was studied differently. So, let me start with the theory that any plane isometry is a composition of at most 3 reflections in lines. First, it is based on following remarks on Feynman that plane isometry is determined by its restriction to any 3 non-collinear points. So it is well-known thing, and I don't want to discuss it. It is, so if you measure the distances to 3 non-collinear points, you know where your point is. And here is a proof of theorem based on this lemma. Assume that we have an isometry that is presented by map of triangles, so we know the image of the triangle. How to decompose it into the reflections. First, let us move A to f of A, where it should be. It can be done by reflection uniquely. If you have reflection in light, then the next step would move your image of B to where it should be without moving A. And after that, it may happen that it is already done. But if it is not, as in this example, it was specifically prepared, then the next step will complete the thing. This theory is generalized to very general setup when you have just n-dimensional space, some classical spaces. Then any isometry can be presented as a composition of at most n plus 1 things. Let us consider now some of them. So, reflections in parallel planes, how it looks. Like that. And you see that this is a translation. Here is the proof that it is a translation. The effects in any situation like that. The decomposition is not unique. Though sometimes we have less translation needed. So the same decomposition can be, the same translation can be obtained if you just move these lines. The only thing which is needed really is that the lines should be parallel to the original position, to themselves, to each other, and the distance should be correct, and the order of them should be as it was before. Similarly, we can play with other lines, let the lines be intersecting in the plane, then we can do the same. And we see that this is a rotation. And here is the proof that this is a rotation. It can be just no was needed, I believe. Of course, everything is written, but
your picture was not a rotation.
Hmm?
The picture was not a rotation. The boat.
What is not?
The boat was not rotating.
The boat?
And because it's 90-degree angle.
I think that I specifically use this 90-degree angle is an angle.
That one is not. That's not the rotation.
They say the rotation of the boat is not equal to the rotation of the origin.
That's not.
It's two sides. It's so funny. This rotation by 90 degrees around this point. Absolutely.
So it is two alpha rotation.
Well, yes, yes. This is the point each time. In the previous situation, also it was not a translation by the distance between lines, but by twice the distance between lines. And here it is twice. And this twice will be repeated many, many times today. Okay. The composition of rotation also is not unique. You can do the same thing. You can move these two lines. The only important thing is that they should have the same intersection point, which is the fixed point of this rotation, of the composition, and the angle between them should be half the angle of the rotation. And you can see how it happens. Now, we have therefore lots of relations between reflections. First of all, each reflection squared is identity. It's involution. Second, in all these examples, we see that two lines could be moved without changing the composition. And here's a theorem, which I wasn't aware about, and I think that this is the first result original in this talk. This is a complete set of relations for the group of atoms. Though, of course, it is a strange subject. It is not considered by algebraists probably as comparable to usual theorems of this sort, because we have a group of cardinality continuum. So the number of generators is continuum, and the number of relations must be in this situation continuum. But a nice thing is that these relations are well organized.
What?
Well organized. They are well structured and they are useful.
Also, you work over other fields, power fields and finite fields.
Yeah, of course. Well, I will stay in the real plane today.
Okay.
Or to see space, where space, it can be done. Now, lemma. The composition of any four reflections of inlines can be transformed by the relations that are listed there into a composition of two relations. And here is the proof. Assume first that the first line is not parallel to the second, and third is not parallel to the fourth. What can you do? You can rotate first and second. This is one of the relations. In such a way that the second would pass through the intersection point of third and fourth. Then I can do the same with the third and fourth lines to make this third line coinciding with the second. And then this 2 equals 3, because it is not correct equality, and we have to delete this line altogether. So that's a joke. But certainly this is, since there is a composition of two reflections involved, so we have a composition of two reflections in two lines. There are other situations. I assume that either first is not parallel to the second, or third is not parallel to the fourth. Then we cannot do this trick that we give the going of two intersection points, but nonetheless we can make one of the lines in one pair parallel to the lines in the first pair, other pair in this way. And after that, we can shift first and second to have the second coinciding with the third, and then we can keep. And finally, the most complicated from this point of view, but the most elementary on the other hand. When we have two pairs of parallel lines, we can rotate two of them by right angle. And, well, we have already the situation on three figures. Generalization of this lemma, not that easy to prove, but I did it. I don't mean to tell you. This is n-dimensional space composition of any n plus 2 reflections in hyperplanes is composition of n reflections. We also can remove two of them. Very similar things. And relations are the same. So relations are borrowed from here. Now,
we have a presentation in RN also.
yeah. In RN, I can do the same with parallel hyperplanes. Translation is expressible in this way, and rotation is expressible as composition of two reflections in hyperplanes. The hyperplanes can be rotated. We have a similar system of relations, and a different theorem by lemma, any relation can be reduced to a relation of length most 3, the composition of a number of reflections reverses orientation. Therefore, 3 is out. And when we have just two reflections, then one of them is inverse to another one, therefore it can coincide with, so this is the first. Okay, generalization of theorem, any relation among reflections in Rn follow from this relation. In other planes, the same holds true. Say, for example, on the hyperbolic plane, we can prove the same theorem. And the third class, it looks impossible because we have different groups, different planes, and they have the same system of relations and generators. So the groups are isomorphic. How does curvature work? How can we distinguish with that? On sphere, everything also holds true, and the reason is that geometry is hidden in this relation. The geometry is hidden in the relations. Which lines pass through which point is a matter of the geometry of these planes. So let me explain this in the following way. Two reflections commute in lines. Commute, yeah?
I just want to make sure I understand M and L and M prime and L prime. So these are lines which intersect at the same angle, so M and L intersect and M prime and L prime intersect.
Or they are parallel.
Or they're parallel.
Yeah, so they belong to the, well, each two lines determine some tensor of lines, and this relation gives, instead of two members of this tensor, two other. When the lines are perpendicular, the reflections commute. And on the plane, if you take two intersecting lines orthogonal to each other, they commute. Take the next one, the second and the third commute. Take the fourth, the third and the fourth commute. And then we have the first and the fourth, we came back. And if this is Euclidean situation, then this angle is right, and they commute either. Otherwise, they do not commute, but nonetheless, we have all these relations satisfied. It's just different geometric situations in four different groups. On the projective plane, a reflection in line has an extra fixed point, so any reflection in line is automatically a reflection in the polar points. So the situation is slightly different, but nonetheless the same. Now, I want to extend the notion of reflections. Reflections usually are just reflections in hyperplane, but I want to consider together with them reflections in subspaces of low dimensions, higher codimensions, in particular. I will speak about involutions. Reflections will be involutions all the time, so transformations of period. And they must be determined by fixed point set, which is really a sort of condition of presence of method. Otherwise, it's not so. Key example is the reflection of line in a point. It is really reflection in point A, but it's formula. And it can be generalized. You can multiply some number of these reflections orthogonally and identity involution, and you can get this reflection in subspace of any dimension. And further, you can generalize this to algebraic spaces, spheres, projective spaces, or other symmetric spaces. So this is also our universe, but we will concentrate mainly for a while on the plane. Line is too simple to deal with this. The correspondence between subspaces and reflections is very shortest connection between geometric objects on one hand, subspace. On the other hand, it is about isometry. So this is the simplest encoding of isometry. That's why it's a nice visual series. Why involutions? Well, involutions also are nice. Because for involutions, the inverse is the same as this involution. The inverse product is just the product in the opposite direction.
So what are the axioms that say an involution is determined by 6.7?
Well, it's not axiom. I will
No, which properties of the space?
Which properties of the space? If, say, you have some bilinear form, and you consider involutions preserving this bilinear form, then it goes through, right?
So for hyperlight space, you have to work in Lorentz space or something? For non-Euclidean geometry, you have to work in Lorentz space to use this formulation.
Which space?
Lorentz.
Lorentz. Oh, yeah.
Lorentz.
Yeah. Okay. But in hyperbolic spaces already good. There is nothing there.
The quadratic form is there. It's non-linear.
Okay. Yes. It's better to go to the vector space. Really, there was some history of this. There was a long process of formalizing Euclidean geometry, starting from Euclid, from its elements, and there were more or less three major systems which appeared as a result of this process. One is the most famous, is David Hilbert's Foundations of Geometry, where Hilbert axioms were sort of developed, enlarged in a very straightforward way. There were some nice outcomes, but overall it's terrible. There's 20-something axioms, that's a large number. Almost at the same time, there was a paper by Herman Weil. Wait, I have misspelled his last name. Sorry. This was a book about general relativity, but the first chapter contained nice foundations of geometry, and it is more or less easy and commonly accepted way now, much less known, but much more popular. The origin is not that famous, but the result is used by everybody. And there was a third thing which is absolutely in shadow. It took longer. It was Friedrich Bachmann who completed this. This is foundations where points and lines are considered as elements of the group of isometries. The properties as elements of group are formalized, axiomatized. It is very elegant because the number of objects shrinks. It is not about that, so it is not duplicated. But from the pedagogical point of view, I don't think it is the best thing to use, because geometric flavor is somehow lost. So replace everything with populations. Certainly you understand it. So there is a vocabulary between algebra and geometry. There is a bridge with two sides.
I can't read the fine print. What year was that? What year was that?
The book was published 73.
What?
73, the last edition of this book. 1973.
Huh? 1873?
1973. So much later. Recently I had a conversation with his PhD student who was involved into this process. It's almost our time. This month. Objects are a group generated by a set of involutions. Involutions are reflections in lines, and they are identified with lines. Lines are perpendicular if the reflections commute. This is just the definition of them being perpendicular. A point is just a composition of such two commuting involutions. And a point belongs to a line if the corresponding reflections commute. Three lines are concurrent or parallel, so they are in the same pencil if the composition of the reflections is a reflection.
Sorry, Oleg, can I just ask?
Yeah.
A point is already a composition of two reflections?
Yeah, it is a reflection, but it is a reflection in a point. And as such, it can be obtained if you take just two reflections in line perpendicular passing through this point and take the product.
But this is confusing because of your second line. You say involutions are lines.
Yeah, they are identified. There is no separately.
Well, what about reflecting on a point? That's also
This is, well, first of all, in the setup we have a group generated by a fixed set of involutions. This set of involutions is called, yes, each of them is called line.
the points are
Yes, and the points.
points are what?
Points are compositions of those involutions, which are lines, if the corresponding involutions commute. If the lines are perpendicular.
Okay, got it.
So there is this.
What about the fifth thing? He's saying a point belongs to a line even only if the reflection can you draw a picture?
Well, of course, here is the picture. A reflection in this point and a reflection in the line can be obtained in this and in that way.
Yeah. Both sides.
Okay. These are different reflections. Well, it's strange but nice. Here is the four axioms, very simple, which determine absolute geometry.
What is absolute?
Absolute means here that it may be positive curvature, zero curvature, or negative curvature. For each of them, these axioms are good. It describes some part of it. What is called absolute geometry?
Oh, the common part.
Common part, yes. But then you have to introduce something else. So, in high dimensions, they didn't do this. So the whole progress was sort of finished just in this book. There were several PhD students who wrote some nice papers about it, and then the whole school was announced to be out of fashion. They moved to different directions. I know this because of Bachman, who belonged to this school. He was not involved into this. His results about moves of triangulations now are used in quantum invariance of three manifolds and something.
Partner, you said?
Partner.
Partner. Yeah.
But he
was one of the students?
He couldn't find a position. No, he was a student of the Meister, I guess. But anyway, this school was sort of considered.
But what he did was fantastic.
Yes. But he couldn't get a position of professor.
It's too good. It's too good.
So it's a digression. It is not related to our subject. Now, let me come back to my say. consider composition of reflections through points. Well, I promise that this will be not only lines. So when you have 2 points, what you can do? You can do this. And you see that this is also a translation. The division of 2 reflections in points is a translation. Here is a point. It is a translation by a vector which is half of the vector corresponding to the translation. It also corresponds to the translation. And since they are related so nicely, we see that this arrow is half. Well, we may speculate about head-to-tail addition. For me, it was a new term. I didn't know that. In Russian, it is called somehow like triangular rule. Here it is much nicer expression. Head-to-tail. Yeah, head-to-tail of another. And here we have also head-to-tail, but for products of reflections. Each time when you have 2 compositions of reflections, and last in the first of them, well, the last in the first of them coincides with the first in the second, it is again a composition of 2. The original head-to-tail, I don't know how to generalize, but this one allows a huge number of generalizations. So, here is this observation. If we have 2 compositions of involutions, and we have this coincidence, then we can calculate the product. Which isometries are compositions of 2 reflections? All. That's right.
I know it for 3. I know it for 3. I know it for R3, so.
Yeah. But this is true in general. For any dimensional case, I wouldn't prove it right now, because I promised that the talk would be, well, let me say, low dimension. But in 3-dimensional case, we will see. So we have another pair of subspaces such that the given isometry is a composition. And this is an analog of arrow representing the translation. So let us do some graphics. If the subspaces do not intersect, then we can find an arrow, the shortest arrow between them, connect them with an arrow. And then consider this A and B as decorations at the end point. The arrow is needed to say which one is first, which one is second. So something like that. Decorated arrow. So at the end point we see 2 subspaces perpendicular to the arrow. If the intersection is not empty, this arrow would shrink to a point, but it is still decorated, so let us take the decorations and connect them with curvy arrow just to say that this one is first, this one is second. Something like that. To what extent the representation is not unique? Well, we can reformulate this question in the following fancy way. We will just introduce an equivalence relation. We will say that 2 pairs of involutions or subspaces are equivalent if and only if the corresponding compositions coincide. And then we can ask, is it possible to have this description, to have more explicit description? How can it be? Well, let us look at the examples. Angle arrows for rotations. Rotation has a fixed point, so whatever the composition of in composition of reflections could be with a fixed point, and so we know already that it is a pair of lines the lines intersect at the center of rotation. The angle between the lines is the half of the rotation angle. And the picture of lines just is a description of this rotation. As usual, arrow is a description of translation. We can rotate them like this. This phase use the same. Now, what is head-to-tail formula for rotation? Given the rotations, present them by angle arrows, and then by these rotations, achieve that the second line of the first angle is the same as the first line of the second, like this. Then erase the common line and draw an arc. So, by the way, this example appeared really in tests for students in geometry course. I asked them to make composition, and this was apparently the simplest way to do it. So this is the full picture for.
I mean, what's nice is the upper two rotations, right?
Yeah.
You compose those and say, well, it's a rotation. Where's the center of the rotation?
Yes.
So that's how you find it.
Yes.
Quite beautiful.
Yes. But be careful, the angles here are half the angles of rotation.
Right.
If you take the full angles, you wouldn't get the result.
You take the half angle, there's the oh.
Yeah. Right. And you obtain the pattern.
It's funny.
Reflections in points. Well, reflection in point is also rotation around the point, about this point, and therefore it can be decomposed, as I mentioned already. And it gives you several new relations. In particular, we can express this reflection in point through rotations, but you can also move the things around and obtain other relations here which may be used. So altogether, these three reflections and identity form the group D2 plus D2. Now let's consider reflections in line and point. The next example. Okay, what is this?
Glide reflection.
Glide reflection, because you can do this like that. And this, indeed, this is a proof. The second reflection in point, can be decomposed as a composition of two reflections in perpendicular lines, one of which may be made perpendicular to the first slide. And then you see that first we have a translation, and then we have a reflection. And this is the standard definition of glide reflection. And certainly you can do this in another way. Yeah, here is the decorated arrow. The decorated arrow is an arrow connecting line and the book. Though you can do this in that way. This means that we can point it as this decoration, and point as that decoration doesn't matter. You can move them if you wish. Both decorated arrows represent the same glide reflection. Decorated arrow of glide reflection may glide along itself. Look. But that's it. You cannot do any more. If you move it up and down, the composition will change because the vector, this arrow, is on the invariant line. So it is frozen.
I'm sorry, I don't understand the meaning of this sentence.
What?
I don't understand the meaning of this sentence. But,
The decorated arrow, which is this one, may glide along itself, along its own line. It may go back and forth without changing the composition. The composition isn't there. Like this. Okay. Now let's take two glide reflections and consider its composition, their composition. First of all, we have to choose the decorated arrows for each of them, and by gliding them appropriately, we put the final point of the first one at the initial point of the second one. It's like in the usual business with arrows representing translations. But now we are more restricted. We can move them only along the lines, which is still enough unless they are parallel. But this is a special case I don't want to consider it now. We may do this as an exercise. Anyway, what we get, and I'm free to move the line at any given point. So I prefer to move these lines outside, not to the first point in the first summand and the second point at the second. So that the common point is just a point, decorated with zero space. And now what we can do, we can just draw oriented arc from the first of this decoration to the last, and erase everything else. So the composition is a rotation. It's a proof, and it's a way to calculate, and it's a way to find the fixed point, and a way to find anything. For an exercise, I suggest to find similar rules for composing rotation and glide reflections in any plane. Certainly it is contained already in this picture. In the three-space rotation, let us take two lines intersecting each other, so they belong to the same plane. And I want to put my ship in a parallel plane, but it doesn't matter. And now, let it go. The final result is a rotation. This is not that well known. People know that rotation in the space is a composition of two reflections in planes. But reflections in lines, if the lines intersect, are not any worse. They are better. But they are more useful. Here is sort of messy proof. You can make all the arguments on this picture. But already I think it was quite obvious. Everything is alike on the plane. A decorated angle arrow is formed by two intersecting lines. So this thing determines the rotation of the whole space. You may think about this also as a rotation of a sphere, but on the sphere, these lines intersect sphere in pairs of antipodal points, so it is sort of a reflection of the sphere in pair of antipodal points, and any rotation of the sphere, which is sort of similar to translation. Now it is a composition of two reflections in pairs of points, and for this situation, so what we have really, what is the graphics? We have an arrow, which is most visible here, So it's a part of great circle, connecting these 2 points. The length of this arc is half of the rotation angle. It is in the plane perpendicular to the axis. And what is funny, here you can, some of them, you can make compositions. The standard thing how people deal with rotations, besides analytical, quaternions and other things like that, but in elementary setup, is to consider what is called angular displacement vector. So you draw a vector along the axis whose length is the angle of rotation. But unfortunately, this thing is not related to algebraic operation. Composition of rotations is not commutative. Summation of angles is commutative. So there is an operation, but very, very complicated in terms of that. And this is a nice equation. Now, screw displacement. This is another isometry of the space, and it can be obtained as follows. So you make 2 reflections in skew lines. Now our lines form an angle, but do not meet each other. They're skew. And this map does not have any fixed point. So to see why it is so, you may do the following trick. You may just take a line parallel to the second one, but intersecting the first one, and take the reflection in it twice, so that it would not affect the whole composition. And then the first 2 give you rotation, and the second, and the last gives a translation, because they are happening in parallel lines. Recurrent arrow presented as cubic displacement is an arrow with 2 perpendicular lines at the endpoints, but these lines are still to each other. So this is the essence of, this is encoding of this screw displacement. And it can be used to make, again, head-to-tail rule. Indeed, if you have 2 screw displacements, you may find for them decorated arrows, find common perpendicular for the lines in the arrows, and by gliding the arrows and rotating them, which is allowed, you do not change anything, you may make this common perpendicular the decoration at last point of the first vector, and the first for the second. So the picture looks like this. So the green, white, and blue is a decoration for the first arrow. The blue and magenta is form decoration for the second. And then what you have to do, well, very natural thing. Draw common perpendicular for the decoration at the beginning and then the end, and erase what is not needed. So the composition is, again, screw displacement. There is a theory of screw displacement which was built in the end of the 19th century when it was really used in mechanics. There was a whole calculus for this screw displacement. Maybe this would be a good contribution to that, but it is too late. There was some prizes by the guy who developed. But more elementary though. Spin. There is a, two-fold coverage for focus. I'm in the last 15 minutes, so I can leave the elementary level, but not part of it. So let's consider, on one hand, the orthogonal group, special orthogonal group, preserving the orientations and rotations of the thing, of n-dimensional space. It has the fundamental group made of two elements, so it has universal powering, two-fold powering, and it is equipped uniquely with a group structure. It is called spin group, and there are explicit constructions here.
So what makes it, when n is 2, of course it's a z instead of a z2. When n is 2, it's a z instead of a z minus 2.
Yeah. Well, n is 2 is a special case.
My question is that the geometric pictures you've been presenting are kind of the same in n equals 2 and n equals 2. So where does it happen?
Well, let me first present this picture, and then we will come back to it.
Okay.
The point is that in n equals 2, the thing is very simple. It's sort of degenerate, and it is much more fun to consider double covering not of the connected components, but of the whole orthogonal group, which is a couple of circles. And this is also two circles, but the group structure there can be defined in two ways. So-called, well, you see, here is letter S, and here is letter S, and they are both there for different reasons accident. But then smart people decided that when you delete one S, then in the other group, you also have to delete this S, and what you obtain is a pin group. There is a nice paper by us here. Here. Well, don't remember that. Both maybe. Where this was done, but there are two groups which are called pin minus and pin plus. They play an important role in topology, different roles, and the group structure is lifted differently. And what I'm going to tell you is related to that. Let me just discuss this simple connected situation. And in the case n equals 2, it is sort of probably the same value. So, how to understand elements of spin F? Since this is a two-fold covering, there is a general way how to understand this, and finish once explaining in details how to do this. Very useful thing. This is useful here. So we have this SRN and it's two-fold covering. So we have here identity, and whatever element here can be connected with the path. So you may take an element here, whatever element here. It is projected to one of the points here, and then you can connect with the path to the identity and leave this path, and the homotopy class of that path determines which point is here, this or that. It could happen that if it was this, then you have to go another way, and downstairs you would follow another way.
Leaving by classes path.
Two. There are two classes because SON in our situation.
Path. Did you say path or
Path. Not loop.
no?
No?
He's concerned that
Two
all paths are homotopic to a point.
Paths are homotopic to the point if you allow to move the endpoints. But if you fix
That's
endpoints,
how that's what it happens.
then yeah, this is a standard definition for homotopy of paths. Otherwise, it's really not interesting, and it couldn't be involved involved into this story, but in this story, certainly we fix the endpoints of paths. So, an element of covering space, if it is a group, can be identified with an element of group downstairs, plus enhanced by a homomorphic class of path connecting this element to the y. And then you can develop even group operation there using this pairs. You can operate with them. So we know now a lot about SON. I didn't tell you, but you may guess that it is also related with reflections and points. SON is generated by reflections in subspaces of codimension 2. Reflection in a subspace of odd codimension changes the orientation, so it doesn't belong to this group. But when the codimension is even, that's fine, and you can use just subspaces of codimension 2, or you may use all subspaces of even codimension. And we know already that elements from SON can be presented as compositions of two reflections, in particular two reflections of this kind. So probably it makes sense to think what is this path in the situation when the corresponding
Composition and reflections, right? How many reflections for SON?
For SON, well, if you consider reflections of fixed dimension, the number of required is growing together with n. But if you allow any number, any codimension, any even codimension, then you can have only two, as it was before. So you can represent maybe again dimension 2 is an exception, because there is no codimension 2, no 3. Yeah. But in high dimensions, when n starts with 3, then you can do. And now for let's consider just the case of subspace of dimension 2. So we have reflection in codimension 2 space. Oh, it doesn't look like codimension 2 even in dimension 3. Reflection in that. And I want to return each point back. So the normal direction is of dimension 2. And I can return it in this way or in that way. And these are the two paths of space. So the direction of rotation can be determined, can be encoded in orientation of this subspace. So instead of the homomorphic class of path of this thing, I may consider just orientations of this line. Now, with composition, it works perfectly. I have no time to discuss this, but if you apply several orthogonal to each other, commuting reflections, the pair of orientations in the original subspaces will give you orientation of the intersection. So orientations of intersection are related to the corresponding class also. So now, for any element in C, the encoding is like that. It is orientation here and there. There's a couple of codimension 2 subspaces which are equipped with orientation. And there are head-to-tail rules like that. Well, now the subspaces, well, the reflections are not involutions anymore, they are of order 4. And when you multiply two of them, when you just make square, you have this unique element of order 2 there. But anyway, the whole calculus is extended there, and you can write the complete system of relations transformed from there. And you can also calculate in this way.
How do you compose two orientations when they're equal?
Well, when they are equal, we still have this picture as a composition. But this means already the same as that, well, in the same line. Double line is the only element of, and it doesn't depend on the direction of this line, on the shape of this line. This unique element in the center. It's more interesting that these two are inverse to each other. It's more interesting that when the orientations are opposite, the corresponding transformations, the corresponding elements in spin are inverse to each other. So I have my time almost finished, and there are many other things. Probably I have to tell you where do I go. I don't know. The whole direction, it is what I'm not a specialist. I'm a new in this field. It's absolutely just a collection of observations. I think that there is observations, and I tried to ask specialists. I couldn't find references to this thing, so probably it is new. Now, what is it about? Why is it interesting? And where to go? Not all the involutions are reflections. They are not recoverable by the fixed point set. But if you add some structure, you can do this. The key example here is SL2R, special linear group of 2 by 2 matrices. It is well known that this is an isometry, well, the projective group is the isometries of hyperbolic space. And hyperbolic space can be obtained if you just take the corresponding involution in this group and consider them with additional structure. So this additional structure are just quadratic folds. This is one of the standard constructions. The construction is repeated for many other groups. I have not yet learned this. For G2, there are several constructions. And if I understood correctly, specialists, they know pretty well the whole picture and theory from the point of view of algebra lead, from the group lead, and its internal geometry. What we use here in the group lead that we studied, there are involutions. They form several conjugacy classes, and they have very nice interaction by the group structure. This interaction probably contains about the same or more as the corresponding dual picture for the algebra. So certainly compositions composing of reflections and calculus with isometries in this geometric way is valuable mostly for low dimensions where you can draw. When you have to use computer, probably it does not matter even when it is not that. Though still it is interesting how these formulas are related to each other. In Bachmann's approach to foundations of geometry, several things haven't been done, and they are conceptual. The gap in higher dimensions is not that conceptual, but there is a conceptual gap in order relations in semi-algebraic geometry there. I think that it can be understood from this point of view. There is a nice observation by Milner. I told him this story, and he, in a week, come back with description how to explain the order on a line in this term. But so after all, I want to have a class in the spring. I don't know if I will be allowed or not, but at least I submitted my proposal.
You do it as an extra activity.
I can do this as an extra activity after all. No problem. Where I want to invite students to play with this, I have to warn from the very beginning that it is not good for PhD. I know. You know why?
Why?
Because nobody does it.
No.
If it will be done good, certainly, maybe whatever, but I cannot promise. But this is a warning. It's not. I don't want to see. Everybody's welcome.
It might be good for a great PhD.
Yeah.
Very original one.
Yes.
That's always a correction.
Well, thank you. That's all.